Hello everyone, am I audible to you? Hello, am I audible guys? Please tell in chat. Hello. Okay, today we'll be discussing CodeChef Starters 202. So let's start with the discussion. Problem A, buying flowers. Chef wants to buy n flowers. He can either pay 4 coins and receive 2 flowers or pay 5 coins and receive 3 flowers. Both types of transactions can be repeated as many times as he likes. Find the minimum number of coins chef needs to pay to buy exactly n flowers. And there are 100 test cases, and for each test case n is 100. So basically, problem A, uh, basically we need to buy n flowers, and we can do two types of transactions, which are 4 coins for 2 flowers and 5 coins for 3 flowers. So let's see the test cases. The first test case is n equal to 2. So since n is equal to 2, we won't be able to do this transaction. So the answer for this test case would be 4 coins. Then the next test case is n equal to 3. We'll need to do this transaction, so 5 coins. Then the next is n equal to 5. We can do one 3 flower transaction and one 2 flower transaction, so 4 plus 5, 9 coins. Then n equal to 8. For n equal to 8, basically if we do this transaction, then we are paying 5 by 3 coins per flower, and here we are paying 4 by 2 coins per flower. So this is basically 2 coins per flower, and this is basically 1.66 coins per flower. So we need to do this transaction as many times as possible, because this transaction is beneficial to us since it is cheaper than this transaction. So we need to maximize the number of 5 coins 3 flower transactions that we are doing. So for 8, what we can do, there are various options we have here. We can let's make a table: 5 coins, 4 coins. So what we can do is we can do zero transactions of 5 coins and 4 transactions of 4 coins. So that would give us 8 flowers. Or we can do one transaction of 5 coins, but when we do one transaction of 5 coins, then there will be 5 flowers left. So 5 flowers cannot be obtained by doing 4 coin transactions. So this is not possible. If we do 2 5 coin transactions, then we'll be able to do one 4 coin transaction. And doing 3 is also not possible, because that would be 9 flowers. So since we need to maximize the number of 5 coin transactions, this would be our best possible answer. So 5 into 2 plus 4, which is 14 coins. So basically the key observation in this problem was to maximize the number of 5.3 flower transaction. So one way to now solve this problem would be simply running a for loop a equal to 1 till a is less than equal to n by 3 and a plus plus, and if n minus a into 3 is even, if is odd then continue, else basically answer is equal to minimum of answer comma a into 3 plus n minus a into 5 plus n minus a into 3 by 2 into 4. So one way to solve this would be this, using this O of n by 3 for loop. Basically what this for loop is doing, A is basically the number of transactions that we are making of 5 coins to 3 flowers. So let A be the number of transactions that we are making for 5 coins to 3 flowers. Then 3 into A would be the number of flowers that we are buying using these transactions. And n minus A into 3 would be the number of flowers left to buy after doing A transactions. So if this number is odd, then we cannot obtain this number by doing the 4 coin transaction. So we just continue, and we can take answer as minimum of answer comma a into 5 plus n minus a into 5 is basically, since we are doing each a transaction in 5 coins, so number of transactions into number of coins per transaction plus the leftover flowers would be n minus a into 3, and dividing this by 2 would give us the number of 4 coin transactions. So divide by 2 and into 4. So number of transactions into cost per transaction. So this was a simple for loop that we can use, which basically simulates this process. We can take an example also. Let's take n is equal to 16. So what this will do is it will check for a equal to 1, 2, 3, 4 till 16 by 3, which is 5. So when a is 1, then b would be, since we can just make another variable n minus a into 3, which is flowers left. So 16 minus 3 13, 16 minus 6 10, then 7, then 4, and then 1. So now number of b would be, in this case not possible, in this case 5 not possible, then 2 and not possible. So for each test case the answer would be a into 5 plus b into 4. Basically this value is b, number of 4 coin transactions. So here it would be, since it is not possible, then 50 plus 20 70, not possible, 20 plus 8 28, and not possible. So this would be the answer for this test case. So yep, and 4 into 3 12, 2 into 4, okay, 16. So 28 would be the answer that we'll get. So basically now this was an answer in O of n, but we can do better in this question. This would pass since the constraints allow it to pass. The time complexity that this solution will take would be n into t, that would be just 1000 operations, 10,000 operations. So this is a passable solution, but we can do better since we have this observation that we need to maximize the number of A transactions. So basically I'm calling this A. So we need to maximize the number of A transactions. So what we can do, uh, for an N, we can do a maximum of N by 3 transactions of A, right? Basically a floor. Whenever I don't specify, it would be floor division only. So N by 3 transactions of A would be maximum, because for example, if N is equal to 16, I can do a maximum of 5 transactions. If N is equal to 18, I can do a maximum of 6 transactions. If I try to do 6 transactions here, then I would be getting 18 flowers, which is more than what we needed. So I can do a maximum of N by 3 transactions of A. And after doing these N by 3 transactions, basically the number of remaining flowers would be N percentage 3 remaining flowers. If I do N by 3 transactions of A. So remaining flowers, if I do N by 3 transactions of A. So let's analyze what happens when at different values of N mod 3. If it is 0, it can be either 2 or it can be 1. It can be nothing other than this, other than these values. So if N percentage 3 is 0, then basically we have got the answer. So the answer would be just N by 3 into 5, because we are basically buying each and every flower at the best price that we can buy. So the N by 3 into 5 would be our best answer. Let's take the case where there are 2 flowers remaining. So in this case, the answer would be N by 3 into 5 plus 4. Basically, since there are 2 flowers remaining, so we need to do another transaction of 4 coins to obtain those 2 flowers. And now if the remainder is 1, then basically that means that we cannot perform N by 3 transactions, because performing N by 3 transactions, uh, after performing N by 3 transactions, we are only left with 1 flower, and we cannot buy just 1 flower. So basically what we need to do is we can do N by 3 minus 1 transactions. So now we will have 4 flowers. After this, we will have 4 flowers remaining. So for 4 flowers, what we can do is we can do 4 into 2. So basically using this set of formula, we can solve the problem in just O of 1. So I'll show you guys the code for this. Basically, if N mod 3 is 1, then the answer would be 5 into N by 3 minus 1 plus 8. So 5 into N by 3 minus 1 plus 8. If N mod 3 is equal to 0, then the answer is simply 5 into A. 5 into A. If N mod 3 is 2 basically, then 5 into A plus 4. 5 into A plus 4. So that was the solution for problem A. If anyone has any doubts in this problem, they can ask. No, basically I was unable to solve min-max Deque with queries, the hard version. I was unable to solve that. I think only 25 people in Div 1 solved that. And the actual solution is also quite complex. It requires binary search on segment trees, I saw after the contest. So I don't think we will be discussing that in today's discussion. Today's contest was quite unbalanced, basically. If anyone has any, yep, easy version we will be discussing. Yes, we'll be discussing the easy version. So, are you guys clear with the first problem? Okay, so let's move on to the next problem. So the next problem is, if only I could read. The median of an array B of length 2m is defined as follows. Sort B in non-descending order. The median of B is then defined to be the element Bm after sorting. That is, the median of B is obtained by sorting it in non-decreasing order and then taking the left of the two middle elements. For example, if B is equal to 2, 5, 1, 2, 4, 3, then the sorted array is 1, 2, 2, 3, 4, 5, and the median is 2. Today, Chef learned about the definition of median, but he wasn't paying attention and missed the fact that the array must be sorted first. So Chef thinks that the median of an array B of length 2m is simply the element Bm without sorting it. You would like to help Chef realize his mistake by providing him with an example. You have with you an array A of length n. Find any non-empty contiguous subarray of A of even length such that Chef's definition of median and the true definition of median gave different results when applied to this subarray. It is possible that no valid subarray exists in which case you must output -1. A contiguous subarray is obtained by deleting some element from front and back. So problem B. So basically this problem states that first of all it has a definition of a median. So median of an even length array actually. So this is basically left of the two middle elements in a after sorting the array. So basically, let's take the example that was given in the test case. 1, 2, 2, 5, 1, 2, 4, 3. So basically, to find the median of an array, we first sort it. After sorting it, looks like 1, 2, 2, 3, 4, 5. And now in an even length array, there are two middle elements. So this one is the median. The left middle element is the median. So basically, the problem is to find an even length subarray which has a median different to the left middle element of the unsorted array. So basically, we need to find a subarray. Let's say that this is the subarray that we need to find. So basically, let's say it has 6 elements. So this is the left middle element currently, and let's say that we sort it, and after sorting we get some elements, and now this is the new left middle element. So we need to find a subarray in which these two elements are not equal. Basically, today Chef learned about the definition of median, but he wasn't paying attention and missed the fact that the array must be sorted first. So Chef thinks that the median of an array of length 2m is simply the element Bm without sorting it. Bm is basically the left middle element. So the Chef would like to realize. So you would like to help Chef realize his mistake by providing him with an example. So let's see the constraint is t is still 500 and n and ai is still 500. So the expected time complexity would be around O of n or O of n log n, because since there is no constraint over the sum of n overall test cases, so basically O of t into n would be the, or O of t n log n would be maximum expected time complexity. N square wouldn't pass, I think, because Tn square would be 500 cube and that would be 125 to 10 to the power 6. So, and the time limit is just 1 second. So 1.25 to 10 to the power 8 would give TLE in 1 second. So basically expected time complexity would be O of Tn or O of Tn log n. So now let's see the test cases. The first test case is 2312. 2312. So let's try to just solve this like brute force. Basically, let's find all the even length subarrays and let's try to find if some subarray has different median after sorting. So 2 3 would be 1, 2 3 3 1 and 1 2 would be three subarrays of length 2, 3 1 and 1 2. Then length 4 would be 2 2 3 1 2. So let's check for this subarray. For this subarray, since it is already sorted, then the expected median and the median after sorting would be the same. So basically this is our first observation. If the subarray is sorted, left middle element, let's call the left middle element as Bn, because that's what because this denotion is used in the question as well. Basically Bm. So if the subarray is sorted, then Bm would always be the median. So basically this cannot be the subarray that we want, and this also cannot be the subarray that we want. Now let's look at this subarray. Now the Bm would be this element, and after sorting this array would look like 1 3, and now the median of this array is 1. So since Bm is not equal to 1, so this array is a valid answer for this given array. This subarray is a valid answer. Let's also check for this subarray. Bm is this element, and after sorting this subarray would look like 1 2 2 3, and the median is 2, and since Bm is not equal to 2, so this subarray is also an answer. So we can output either 1 2 3 4, so we can output either 2 3 or we can output 1 4. Both would be considered as correct answers. So 1 4. Yep. So let's see the next test case, 3359. 3359. So the different subarrays in this test case would be 3 3, 3 5, 5 9. This and this basically, and then 3 3 5 9. So basically again in cases of sorted arrays, the median and Bm would be the same. So this cannot be a valid subarray because it is sorted. This also cannot be a valid subarray since it is sorted. This also cannot be a valid subarray since it is sorted, and this also cannot be a valid subarray because it is sorted. So basically from this test case we get intuition to the problem. We get another observation. If the given array A is sorted, then all the subarrays of A would be sorted as well. So basically since here 3359 was a sorted array, right? So all of its subarray would always be sorted only, because in a sorted array ai is always less than or equal to ai plus 1. So in all the subarrays this property would be followed. So all the subarrays would always be sorted only, and in a sorted array the median will always be the bm element. So basically there would be no answer to a sorted array. So from this we can say that for a sorted array the answer is -1, right? So let's see the last test case also. 54545 and 54545. So the even length subarrays would be 54. This one, just a second, 54. This one, 54. This one and this one, 4545. 4545. And these two, 5454 and 4545. So 5454 and 4545. So let's first cross out the sorted subarrays. So this is sorted, and the rest could be a potential answer. So let's see this test case. So in this test case, the first element would be the bm, and after sorting it will look like 4 5, and this would be the median. So bm is not equal to median, so this would be a answer. This would be a valid answer. Now let's look at this subarray. So expected bm would be this, and after sorting it will look like 4 4 5 5, and again the median is 4, so this cannot be an answer. And this is basically bm would be this, and after sorting 4 4 5 5, so the median is 4 and bm is not equal to 4. So these two can be two valid answers. So we can and this also, because this and this are same. So basically the answer could be 1 2 or 3 4. Sorry, 1 not 1. Yep, 1 2 or 1 2 3 4 or 2 5. So basically these three can be all three are valid answers. Any of them you can output. So 2 5. So basically we saw a similar kind of test case above as well. So a similar kind of subarray here 3 1, and here also 5 4. So basically another observation, another intuition that we get from these test cases is that for 2 length subarray, if v1 is greater than v2, basically I am calling this element as v1 and this element as v2 for a 2 length subarray. So if v1 is greater than v2, then that can be an answer. Then that subarray is an answer. How? We can prove this very easily. So let's take v1 v2 and v1 is greater than v2. So this would be the bm element, and after sorting this array would look like v2 v1, and v2 would be our median. So bm is not equal to v2, and hence this would be a valid subarray. So this is another observation. So the last observation that we made was if the given array A is sorted, and then all the subarrays of A would be sorted as well. So what is the condition for a given array A to be sorted? For a given array A to be sorted, AI should always be less than equal to AI plus 1 for all I belongs to 1 to n minus 1. Right. So for these for arrays that follow this property, we can say that the answer is minus 1, right? We found out this above. So let's take the array which does not follow this property at some index I. So if some array is not sorted, then ai would be greater than ai plus 1 for at least one I belongs to 1 comma n minus 1. So at least one I, this property is followed, and if this property is followed, then we can say that ai and ai plus 1 is a valid answer. So basically we proved this here, that if v1 is greater than v2, then v1 v2 is a valid answer. So if the array is not sorted, then there must be one index where ai is greater than ai plus 1, and then that index would be the answer. So we have solved the question. So the solution to the question would look like this: if array is sorted, then no, basically minus 1. Else we can check for I equal to 1 to n minus 1. If ai is greater than ai plus 1, then cout I plus 1. So that was it for the question, and this solution would just require O of n time complexity, which was the expected time complexity to this problem. So I'll show you guys the code now. So I input n and then the vector v, and I'm maintaining a check variable which tells me if I have found the answer or not. And if there is some index where this condition is followed, then that would be the answer, and I mark check as true. And when I mark check as true, this loop is exited automatically. And then if at the end of the loop check is still false, then that means the array was sorted, and then I would output minus 1. So that was the solution for B problem. So if you guys have any doubts, you can ask. Why not I equal to 0 to n minus 1? Basically, I was taking for one based index. Basically, if I put n minus 1 value, if I take, basically I am doing this for one based indexing. So in one based indexing, basically I need to take from 1 to n minus 1. I cannot do from 1 to n, because then if I put I equal to n, then it would be an is less than equal to an plus 1, and an plus 1 does not exist. So when we will be writing this condition for 0 based indexing, then it will look like this: I plus 1 for I belongs to 0 to n minus 2. We cannot take n minus 1, because then an minus 1 would be less than equal to an, and an does not exist in a 0 based index array. So this would be for 1 based, 0 based. And in the code also, I have written the condition I is less than n minus 2, which is basically till n minus I is less than n minus 1, which is basically till n minus 2. So this is for 0 based. Okay. What if all 2-length subarrays satisfies the chef's condition and the answer lies in 4-length subarray? Basically, if all the 2-length subarrays satisfies the chef's condition, so that must mean that Let's analyze the case where all two length subarray satisfy the condition. So what does this mean? For all two length subarrays, V1 is always less than equal to V2, right? So that means for all AI, AI would be less than equal to AI plus 1 for all I. So basically, if all two length subarrays follow this property, then this will be true. And if this is true, then that means that the array is sorted. And if the array is sorted, then that means all the subarrays are sorted. And if all the subarrays are sorted, then none of them follow. I mean, all of them follow. All of them follow the chef's condition. Follow the condition. So basically, the answer would be -1. Did you get it now? Why only checking for two length subarrays would give us the answer? Okay, so now let's move on to the next problem. If I'll just wait for a minute more. So if you guys have any doubts, you can ask in this problem. I did the same approach, but it went wrong. Don't get discouraged. Basically, approach is what matters more in contests in CP. So if you're getting the correct approach, then surely you'll improve quickly. So I don't think you guys have any doubt. So let's move on to the next problem. Yes. So min-max TQ easy version. So consider an array A of length n and n is odd. Alice and Bob will play the following game on it. Let B be an initially empty array. Alice and Bob take turns playing, with Alice going first. So on the ith turn, the current player will choose element AI and insert it to either the beginning or the end of B. So Alice will place AI A1, then Bob will place A2, then Alice will place A3, and so on. So this continues till all n elements have been placed in B. And once the game has finished, Alice's scores is defined to be minimum of B1, Bn. So Alice's objective is to maximize her score, while Bob's objective is to minimize Alice's score. So define FA to be the final score if both players play optimally for the starting array A. So you are given an array A of length n where n is odd, and there are q points update to this array. However, in this version, q is 0, so we don't need to do that. And the constraints for this problem are t is less than equal to 1e4 and n is less than equal to 2e5 minus 1, n is odd, and ai is restricted to 1 to n. So the sum of n all over across all test cases won't exceed 2e5. So basically, since sum of n is overall test cases does not exceed 2e5, then the expected time complexity for this problem, we can assume that it would be O of n or O of n log n at max. So we will try to solve this in O of n log n. So let's start the discussion for this problem. Problem C. Basically, Alice and Bob are playing a game where you have an array A with elements A1, A2 till AN, and Alice and Bob take places. So basically, what we need to do is, first Alice will move and Alice will place the element A1. Then Bob will move and Bob will place the element A2 either before A1 or after A1. So let's just say that Bob placed it before A1, so A2. And then again it's Alice's turn, and so Alice will have two choices now. Alice can either put A3 here, or Alice can put A3 here. So let's say that Alice put A3 here. Then then it's Bob's move. So Bob will place A4 here or here. So basically, Alice and Bob's can take turns like that, and in the end, the score of the array would be minimum of A1, AN. And Alice basically wants to maximize the score. And Bob wants to minimize the score. So we need to tell what is the final score minimum of A1 to AN. Basically, Alice's objective is to maximize, while Bob's objective is to minimize Alice's score, and define f of A to be the final score if both players play optimally for the starting array A. So we need to tell what is f of A. So let's see the test cases. The first test case is 1, 2, 3. 1, 2, 3. So since it would be Alice's turns first, so Alice will place 1, and then the next element is 2. So Bob can, it does not matter actually if Bob places 2 here or Bob places 2 here. And then again it's Alice's turn to place 3, and since now Alice wants to maximize the score, right? So what Alice will do, Alice wants to maximize A1, AN. So what Alice will do is place 3 here, and in this case, if Bob would have placed 2 here on this side of A, then Alice would have placed 3 here. So in both the cases, the final score would just be minimum of 2, 3, which is 2. That's means 2. So the next test case is 1, 2, 2. 1, 2, 2. So again Alice places 1. Then Bob can either place 2 here or 2 here. Then again we have 2, and now since this was Alice, this was Bob, and this is again Alice. So Alice wants to increase the score, so it will place 2 here in this case and 2 here in this case, because if Alice had placed 2 like this, then the minimum of 2, 1 would have been 1. So that would not be good. So basically Alice would be removing this minimum element from the end of the array. Since this element is small, Alice would want to remove that element, right? So in order to remove the small element, Alice would place 2 here on this side. And similarly, in this case, Alice would want to remove this small element from the beginning of the array. So Alice would place 2 here. So answer for both the test cases would be minimum of 2, 2, which is 2. So 2. And the next test case is 1, 1, 2. So again 1, 1, 2. This would be Alice, Bob, Alice. So Alice would place 1, then Bob will place 1. It is symmetrical, so the array would be same. And then Alice could place 2 here, or Alice could place 2 here. Both are the same cases. So minimum of 2, 1 would be just 1. So answer for this test case is 1. So the next test case is 3, 4, 1, 5, 3. 3, 4, 1, 5, 3. So basically Alice would place 3 here, and then Bob can either place 4 here or Bob can place 4 here. Then Alice would have 1. So Alice can place, Alice would like to place one, Alice would basically, Alice, there could be two cases, right? So Alice can either place one like this, or Alice can place one like this for this case. So which of them is beneficial for us? Because in this case the border elements are 1 and 3, and in this case the border elements are 1 and 4. So this is clearly worse than this, so this is better. Since Alice wants to maximize the border elements, so this would always lead to a better answer, since the border elements in this cases are better than in this case. So Alice would be placing one towards here, and in this case symmetrically Alice would be placing one towards here. So if Alice had placed in here, then the border elements would have been 1 and 3, but if one is placed here, then the border elements are 1 and 4. That is better. So basically now it's again Bob's turn. Alice, Bob, Alice, Bob, Alice. So now it's Bob's turn, and Bob wants to minimize the answer, right? So in this case Bob has two turns. Bob has two choices. It can either place 5 here like this, or it can either place 5 here like this. So in this case the border elements are 5, 1, and in this case the border elements are 5, 4. So clearly Bob doesn't want to increase the border elements, right? Because it wants to decrease the final score. So there is like no good in putting a greater element at the border. So basically Bob would be following this path and ignoring this. Also symmetrically in this case Bob would place 5 here, 5, 1, 3, 4. So first of all, one observation I am making, because Bob are basically that only the border elements matter. Basically Alice and Bob won't be making decisions after looking at the elements that are in the middle. They would only make their decisions, only the border elements are those that matter. So basically we get this intuition from solving these test cases, that only the border elements are those that matters. And basically if there is some array where 4 and 1 is the border, and there is some array with 1 and 4 as the border elements, then these two are basically equivalent. These two won't change the answer. Both of them are pretty much the same. So if I am going to place the next element here in this case, I can place that element here in this case. So these two are pretty much equivalent. So basically after the first move, basically 4, 3 and 3, 4 would be equivalent to each other. We can get the same answer from both of these. So we don't need to do this analysis. We can just do analysis on this. So we have reached till the point 5, 4, 3, 1, and now it's Alice's turn, and it has the element 3. So now we can either place 3 here, or we can place 3 here, right? So obviously after making this move, 3 would be one of the border elements, right? After making this move, 3 would be one of the border elements. So what Alice can try to do is maximize the other border element. So since we know that 3 is going to be one of the border elements, so what we can do is we can try to maximize the other border element when Alice is playing. So to maximize the other border element, since we have two border elements 1 and 5, so to maximize the other border element after making the move, what we can do is we can put 3 here, so that the other border element is 5. If we had put 3 here, the other border element would have been 1, and we don't want that. So basically we'll put 3 here. So the final array would look like this: 5, 4, 3, 1, 3, and 5, 4, 3, 1, 3. So answer would be 3, minimum of 5 and 3. So another observation that I made is basically after the ith move, ith AI would be one of the border elements, So basically using this observation, what we can say that when Alice is moving, it can try to maximize the other element, and when Bob is moving, it can try to minimize the other element. So basically this is the optimal strategy that they both will be using in this game. So optimal strategy. Let's solve another test case to get a better intuition of why this strategy is optimal. So let's take the next test case 34251. 34251. So again 3 then 4, since Alice Bob, Alice, and if 3 4 and 4 3 are basically more or less the same. So let's say that 3 4 was the array, and now it's Alice's turn to place 2. So Alice would have two options, to place 2 here or to place 2 here. So obviously Alice would place 2 here because now the border elements would be 2 and 4. If he had placed here, the border elements would have been 2 and 3, which is not better than 2 and 4. So Alice would obviously place 2 here. Now it's Bob's turn, and Bob will place 5. So basically it will try to minimize the other border element, because 5 would be one of the border elements after this move. So Bob will try to minimize the other border element. So in order to minimize the other border element, there are two choices for them. The other border element could be 2 or it could be 4. So since Bob wants to minimize, it would choose 2 as the other border element and place 5 here. Now again Alice has 1 and it wants to maximize the other border element, and it has two choices, 2 and 5. So it will choose 5 as the other border element and place 1 here. So basically 1 5 would be the final array, and answer would be minimum of 1 5. So which is 1. The last test case is 34215. 34215. Again, first of all 3 4 would be the starting array, because A B A. Now it's Alice's turn. Alice wants to Alice would be placing 2. Alice would want to maximize the other border element, so Alice would place 2 here, so that 4 is the other border element. Next turn is Bob's. Bob has to place 1 and wants to minimize, so Bob would place 1, so that 1 here, so that 2 would be the next border element. Now Alice will have to place 5, and it wants to maximize the other border element, so it would place 5 here, so that 2 is the other border element, and then the answer would be minimum of 2 5, which is 2. So 2. So let's formalize this strategy a little bit. Now since we know that only the border elements are required to make the decision, so let's assume that x comma y are the border elements, and it is ith move. It's the ith move, and Bob is moving. Alice is moving. So if Alice is moving the ith move, so basically there can be two scenarios after the move. So initially the border was xy, then what could have been the next new scenario? It could have been ai comma y, or it could have been y comma x comma ai. So we would like to choose the better option out of these. We would like to choose the case in which the other element is maximum. So what we will do, we will choose the case ai comma y if y is greater than x, or if x is less than equal to y. We'll choose this. So basically, and since x comma y and y comma x are pretty much the same, so what we can say is from x comma y we will after the ith move, if Alice is moving, it will look like this: ai comma maximum of x comma y. since we'll be choosing the maximum out of those, and the other border element would be AI. So if if it is Alice's move, this would be the new border elements, and if it's Bob's move, so if it was XY initially, then after Bob would move, AI would be one of the border elements, and the other border element should be minimum. So Bob would choose the minimum out of X and Y. So this would be the transition for Bob, and this would be the transition for Alice. And after all the n moves, we can just print out minimum of both x comma y. This would be our answer. So time complexity required to solve this question is O of n, which we expected before solving the problem. And basically how we will do this, we will initially maintain a pair of a1 and a2 elements, and then we will apply a for loop I equal to 3 till I is less than equal to n I plus plus. So if the current move is Alice, then what we can do is AI comma maximum of a1 a2 would be the answer, and if Bob, AI comma minimum of a1 a2 would be the new border elements. Basically a1 a2, we should actually write this as p1 p2, denoting the elements p1 and b1 b2, actually border 1 border 2. So let's just denote border 1 border 2 border 1 border 2, which was initially a1 and a2. So this, it would look like this after Alice move and after Bob moves, and after this for loop we can just answer would be equal to minimum of border 1 border 2. So I'll show you guys the code for this. So initially the borders would be v0 and v1. Basically I am taking input in a zero based vector. So v0 v1 would be the input, would be the borders initially, and then from 2 till n we will perform the moves. So if I percentage 2 is 0, so that means it is Alice's move. So if it is Alice's move, what we will do is we will replace the smaller element. So if the first element was smaller, then we change the first element to be vi, and if the second element was smaller, then we change the second element to be vi. And similarly in Bob's case, we will change the maximum element. So if the second element is maximum, we'll change that border, else we'll change the first border. So, and in the end, minimum of p dot first and p dot second would be the answer. So this was the solution for problem C. If you guys have any doubts with the explanation, please tell. I went with greedy approach, like Alice will place number on the side which has small number, and Bob will place number on the side which has greater number. Yes, you would have to, this would be the optimal strategy for Alice and Bob. No, Bob will place it on the other side 1 3 4 5. Did I make some mistake while solving some test case? 1 3 4 5. Oh, yep. Actually, no, 5 won't be coming here. 5 will be coming here. We placed 5 on the left side of 4. So here also we'll place 5 on the side of 4. Yes, actually I made that mistake. Yes, you are right. Thank you, guys. So you can ask if you have any doubts. I thought this is DP and I don't get how to approach this type of questions. Please tell how to approach. You can try solving the test cases that will somehow that will a lot of times help you get the intuition required to solve the question. So always try to solve the test cases by hand. When will be DEF? Basically, D is a little hard question, little harder question. It requires segment tree with binary search, and I myself was not able to solve that during the contest. So we'll not be discussing that. I think only 25 people solved it in Div 1. So, yep, we'll not be discussing that currently. So I think you guys don't have any further doubts. So let's end with the discussion. Thank you.